Okay, so how is everyone today?
Good.
Good? All right. So we ended and we were talking about parametric equations, and we're still talking about parametric equations. And we were considering the following specific parametric equations. That x is t squared and y is t cubed minus 3t. If we were so inclined, we could plot a whole bunch of points, and that'd be sort of laborious. But skipping that bit, you can imagine plotting a bunch of points. Notice that because x is t squared, that means that only non-negative x's are permitted, which is to say none of the graph is going to have a negative x coordinate, right? And similarly, or alternatively, because that's a t cubed minus 3t, can t cubed minus 3t ever be negative?
Yes.
Yeah? Because like if you plug in, say, like negative 100, then that'd be negative 100 cubed, which is a big-ish negative number, right? So if you were to make such a plot, you'd notice that in the first place that there's a point here and a point here. So of course that's the origin, that's 0, 0, and this point is 3, 0. And you would observe the following. So something like this. Something like that, and I'm going to remove that arrow there. So you'd observe something thus. So the only thing I want to point out is just algebraically, why is it entirely to be expected that there should be no plot on the left side? Why is there no plot over here?
T squared is real negatives.
Right, because x is t squared. The horizontal coordinate is something squared. All right, and then last time, we said, well, look, the plot intersects itself there. So if you can imagine, being like a little fly or something, and you're flying around and making this trajectory. So you're flying. You go through 3, 0 twice. So one of the times you'll have a tangent that's kind of has positive slope. And then one of the times you'll have a tangent that has a negative slope. And what we were figuring out last time is, how can we find that? So to review that idea, we said that one of the consequences we found is that dy dx, if you wanted to differentiate y with respect to x, now that's a bit of a heartburn involved, because, well, if we want to differentiate y in terms of x, each of those is defined in terms of t, right? So we don't have a formula for y in terms of t. Y in terms of x. Rather, we have them both in terms of t. So if we want to find dy dx concerning the chain rule and other things, the formula is dy dt divided by dx dt. Okay, so then doing that quickly, dy dx, the formula in terms of t should be what? 3 what? T squared, sorry, my brain was just paused there for a second, and then minus 3, and then over 2t. All right, then we answered a question, please find the tangent at both times that you cross 3, 0. Okay, so find the slope of the tangent. So find slope of the tangent for both crossings of 0, 3. 3, 0. Now that's, again, a bit of an issue because, well, we know the x-coordinate is 0. We know the x-coordinate is 3 and the y-coordinate is 0. But our formula for the slope is not in terms of x's or y's. What's it in terms of? T. So in order to address the question, find the slope of the tangent at both crossings of 3, 0, we need to know at what times does that occur, right? So the first order of business is we need to find the t's, and how many do we expect to find? Well, that's how we'll find it, but how do we expect to find it? Yeah, how many do we expect to find? 2 of them, right? Find the t such that that's our location, which means that we need to solve the system of equations x. Well, what do we want the x to be? 3, right? And then what do we want the y to be? 0. So we need to solve this system, but now we know formulas for x and y in terms of t, so that means we want to solve the system. T squared is 3, and t cubed minus 3t is 0. And we want to solve this for t. So, doing that quickly. And if I name this equation 1 there, and that one equation 2, of course equation 1 is pretty straightforward, right? So from equation 1, we immediately determine that t could be negative square root of 3, or t could be the square root of 3. So the number of solutions, that's expected, right? Because we expected to find 2 of them. But to make sure that what we're doing is legitimate, we should also check that they also solve equation 2, right? Because what if they solve equation 1 but not 2? It's the system that needs to be correct, both of them. So we'll check. Checking 2. So I'll check first the negative one. So negative t is negative square root of 3. So that would be negative square root 3, cube that, and then subtract 3 negative square root of 3 equals 0. All right, so we're cubing, so the negative doesn't go away, but we're doing square root of 3, square root of 3, square root of 3. So there's 3 of them, all multiplied. So 2 of the square roots of 3 combine to become a what? A 3. So this first term reads negative 3 and then square root 3. And then we're subtracting, but that's a negative right there, so that ends up being an addition. So that would be plus 3 square root 3 equal to 0. So is that true? It is. So we're good to go. And then, you do this one too. So do this too. And then, okay, fine. So we really did find the 2 times that we crossed that point. So now, to answer the question, we want to find the slopes of the tangent lines. So at t is negative square root of 3. We want to find the slope. So how do we do that? Yeah, plug it in there. So we'll take dy dx, and then when you have like a function like f, and you want to say f of 5, that's pretty straightforward. You just write f and then open parentheses 5 close parentheses. But this is not really it's not the same notation. So you have to have a notation which means I want to take this thing and I want to evaluate it at that t. So the notation for that is you write this vertical bar and then t equal negative square root of 3. So that means evaluate the preceding thing at negative 3. All right. So that would be 3 multiplied by negative square root 3 squared, subtract 3, and then divide by 2, multiply negative square root 3. Okay. Squaring that, the negative squares away. That's a 3. Multiplied by 3 is 9. Minus 3 is 6 in the numerator. So that'd be 6 over negative 2 square root 3. And then I can form a little bit more simplification. 6 over 2 is 3. So you could write it like this. Negative 3 over the square root of 3. You know, and if you felt so inclined, you could rationalize the denominator, but I'm not so worried about it. So that's the slope. That's the slope. So which of the two possible tangent lines, which one does this correspond to? It corresponds to the one where we're going down, right? Sloping down because the slope is negative. Okay, and then at t is positive square root of 3. You know, you'd do it again. Go through a very similar evaluation, and you would determine that it's 3 over square root of 3. Okay? So now, here's a different question. So concerning that plot there, are there any places where the tangent is horizontal? Where the tangent line is going to be horizontal? Right, so, and how many such places will the tangent be horizontal? 2 of them, right? 2 of them. There's going to be a horizontal tangent here, and there's going to be a horizontal tangent here. Okay, so there's two horizontal tangents. So my question is now, find the t such that there's a horizontal tangent. All right. So that means we need to solve an equation. What equation do we need to solve? dy dx is what?
0.
Is 0. So we want to solve dy dx is 0, and we're going to solve for t, right? All right. Well, luckily, you know, we've got it there. So that would be 3t squared minus 3 over 2t equal to 0. All right. So do you observe that this what am I trying to say? That this equation is defined at all t except t is 0. So it's not defined at t is 0, but it's defined at all other t's. So then, noting that to myself, I'll multiply both sides by 2t. Which has the effect of canceling the 2t. The right-hand side is still 0. If I factor a 3 out of that, then it'd be 3 and then t squared minus 1. But then how does t squared minus 1 factor? Very good. So that we obtain the equation 3 t plus 1 multiply t minus 1 equals 0. Of course, we can divide away the 3 so that we get the equation t plus 1 multiply t minus 1 equals 0. And so, you know, there's 2 solutions. T is negative 1 or t is positive 1. Now, I won't do it here, but I'll just let you know that it's conceivable that I could ask the following. I could say, find the equation of that line, say. So how would you go about doing that if you wanted to find the equation of the line? Say, find the equation of both of them. Well, in the first place, you know that they're horizontal, right? So what's their slope? 0. So whatever the equation is, it's got to be of the form y equal to a constant, right?
1 and negative.
Are they? I don't know. So, well, let's consider. So, okay, so I'm getting not good vibes from y'all, so I'm going to go ahead and do it. So find find the equation of these horizontal tangent lines. Now, because they're horizontal, that means that the slope is 0, so they have to be of the form y equals some constant. So how do we figure out that constant?
Plug in t.
Yeah, we plug in the t. So for in the case that t is -1, we'd want to plug that into y. So y evaluated at t is -1 would be -1, cube that, subtract 3 multiply -1. Well, that's a bunch of negatives, but that's -1, and then we're subtracting -3, so that's -1 plus 3, so that's 2. So that means that one of those horizontal tangent lines has equation y equal 2. What do you suspect about the other one?
Negative.
It's going to be -2. All right, good. So again, concerning this this picture here, we could ask, well, what about vertical tangent lines? Yeah. So are there going to be any vertical tangents in this picture? Yeah, right? So, you know, this one is a horizontal tangent. This one is a horizontal tangent. Is there a vertical tangent? Sure. Right there. And, you know, if you have access to the picture, then that's nice. But what if you don't have access to the picture? What if you don't know what it looks like? I just give you some crazy formula, and all you have is calculus at your disposal. Sorry? The slope's going to have to be undefined. But it's not just that the slope's going to have to be undefined. It's not just that. There's actually, it's a slightly more complicated than that. So let's consider. What if I say that this is, what were we doing? A, B, C. So C, find the vertical tangents. Find the vertical tangents. So now there's a lot of different ways in which slope can be undefined. So for example, in your mind's eye, imagine absolute value. It's a v, right? Pointy at the origin. Does it have a tangent at the pointy place? It doesn't. So the slope is undefined for absolute value at the origin, yet the tangent is not vertical, right? So it's not enough that it should be vertical. So find a vertical tangent. In this case, what we need is we need to do two things. We need to solve. Well, solve is not really a good way to say it. We need to. What's the best way to say it? We need to find where dy dx is undefined. So that's necessary, but not sufficient. Okay, so it's necessary because a vertical tangent this will be undefined, but it's not sufficient because this is undefined for absolute value. And we need to say and. Furthermore, suppose that you find such a t, you'll have to say and the limit as t goes to c has to be of dy dx has to be infinite. But there's actually an easier way. There's an easier way. How do we find a horizontal tangent? When dy dx is 0, right? When dy dx is 0. But after all, you know, dy dx, here we have that formula for it, and it looks like that. The reason why it looks like that is because, after all, y is not actually a function of x. They're actually both the functions of t. So what if we just switch the roles? What if we just switch the roles of x and y? So to find the horizontal tangents, we found where dy dx was 0. I claim that we can actually, to find the vertical tangents, we can find where something else is 0. dx dy, right? Because there's nothing sacred about these names. There's nothing sacred about a name, right? So rather, you know, this is enough to make one sad. So rather than that, let's instead solve dx dy equal to 0. Okay. So, but that requires you to understand, well, what's going to be the formula for dx dy? Well, abstractly, it's got to be this. So dx dy must be dx dt divided by dy dt. And of course, that just means the reciprocal of the thing that you calculated a couple, just a few minutes ago. So as a result, dx dy will be what? Yeah, it'll be 2t, and then divided by, yeah, 3t squared minus 3. Okay, good. So for entirely analogous reasons, or by looking at the picture, what's going to be the solution to this equals 0? T is 0. dx dy equals 0 implies t is 0. All right. And that's expected. Okay. So now I could ask the question, how about when is the plot going to be concave down, and when is the plot going to be concave up? So, no, I mean, you can have positive slope but not be concave up. So, for example, square root has positive slope, but it's concave down. So, to remind you of this, so now I'll insert a remark. Is that dy dx, what it does is it measures the slope of the tangent line. So if we have a situation like this, and you've got your favorite input C here. Then right there at that point, there's a tangent line. Now, because that's a line, it's got a formula, and because it's a non-vertical line, it has a formula: y is mx plus b. Right? What the derivative is saying, is that dy dx evaluated at x is c is m. That's what that's saying. It's sort of a way to pick out that m there, to pluck it out of the ether. All right. Now, the second derivative. The second derivative. D squared y dx squared. So dy dx measures the slope of the tangent line. What does that one measure? So we call it concavity. That's its name. But rather, I'm going to say something that is not usually said in a, pardon me, 2,000 level course, but I'm going to say it anyway. What this one does is it measures, it needs an E, the concavity of the tangent parabola. What? So specifically, if I take a picture, and if I choose my favorite input, so what the tangent line is saying is that, you know, if you were really small compared to the red world and you had to walk around on the red world and you wanted to ask what would be the equation for the world if the world really was flat? That's the answer to the slope of the tangent line. So the equation of the world would be that. Now, what if you're really small? What if you're really small and you're looking at that and you want to say, well, I'm pretty sure that the world is not actually a parabola. I'm pretty sure it's not actually a parabola. But if it were a parabola, then what is the best parabola that I could possibly approximate the world with? So it's going to end up looking like this. Like that, right? So that's, you know, the tangent parabola. Now, because that's a parabola, you know, every parabola can be, just like every line can be written as y is mx plus b, every parabola can be written how? ax squared plus bx plus c. Okay. Now, what's the, if you were to differentiate ax squared plus bx plus c, the first derivative would make that c go away, right? Because it's a constant. And then you'd have this b hanging out, and now that would be constant. And then if you differentiate again, that b would go away, right? And what would remain? In fact, not just a, but actually twice a. So what the second derivative is saying, it's saying that if you take the second derivative, d squared y dx squared, and evaluate it at x is c, then the answer is twice a. That's called the concavity. So you can make a tangent line, you can make a tangent parabola, you can make a tangent cubic, you can make a tangent whatever you like. So it's this leading number that's related to whatever the derivative is measuring. So, like, you know, this is called slope, this one is called concavity, and then some of the other ones have names, like the third derivative, if you know, in a physics contest, is called jerk. Actually, it's kind of funny, and you know, they go on. But at any rate, if you calculate the seventh derivative of a function at a point, what you're saying is that well, let's attach the best possible seventh order polynomial to the world at that point. So first derivative, first order polynomial. Second derivative, second order polynomial. Third derivative, third order polynomial. That's what it's saying. Okay. So in some sense, we're asking about, you know, what if we attach the tangent parabola? What's going to be twice the leading coefficient? That's what concavity is asking. Now, to that end and to that extent, what I want you to observe is that the formula that we have written down for the first derivative, well, I guess before I get too far away, is that is that by the end of this class, we're not going to be talking about just tangent lines and tangent parabolas and things like that. We're going to be talking about tangent other things. So, for example, we'll be interested in talking about tangent circles. In this case, the name of the measurement is called curvature. But in general, you can consider tangent anything. So you just say, well, my favorite shape is a line. Okay, and then you consider tangent lines. Or you can say, no, I like circles. So you can consider tangent circles. But you could do tangent bananas or whatever you want. Okay, so this is this dy dt divided by dx dt, like that. But I want you to sort of view this in a slightly different way, and that is that, of course, dy dx is just a fancy way to say x derivative of y, which means that you could write it like this. So d dx of y. What if you wanted to compute the x derivative of y? So that's a right arrow, so that's and implies. This is saying that, well, if you wanted to compute the x derivative of y, then what you should do first is compute the t derivative of y. So do that first. And then once you've computed the t derivative of y, now do what? Yeah, now you're going to have to fix it up by dividing by the t derivative of x. You know, because in a sense you're saying, well, I want to differentiate y with respect to x. And then you say, well, it's not written in terms of x. I can't really do that. It's written in terms of t. So this is saying, okay, well, go ahead and differentiate it with respect to t. Go ahead and do that. And then to fix up that problem, divide by the derivative of x with respect to t. So now, that being said, the question is that what if we wanted to calculate, what if we wanted d squared y dx squared? What if we wanted that? Well, understand what this means. This is saying that you want to compute the x derivative of what? What goes in there? Yeah, you want to compute the x derivative of dy dx. That's what you want to do. But you know, dy dx is not written in terms of x. It's written in terms of t. So what do we have to do? Yeah, we're going to say, okay, well, if it's written in terms of t, go ahead and differentiate it with respect to t. Go ahead and do that. So differentiate it with respect to t. But you know, that's not going to be quite right. So to fix it up, what do we have to do? What do we have to do to fix this up? Yeah, we had to divide by dx dt, so same thing. So that's the formula for d squared y dx squared when x's and y's themselves are defined in terms of t, some other thing. Okay, so this is a formula you must memorize, or you must be able to derive, you know, immediately. So to that end, I can now go back to the question. Back to x is t squared, y is, what was it? T cubed minus 3t. And then ask. Back to that, you know, we had established that dy dx is, what was it? It was 3t squared minus 3 and then over 2t. So we don't have enough time to really get into it a lot, so I'll just say the real question would be find the t where we have concave up, and find the t where we have concave down. But that's sort of a secondary task to actually finding d squared y dx squared. So that's sort of the main task. So how do we calculate that then? d squared y dx squared. How do we calculate it? Well, that formula, right? So we'd calculate the t derivative of that. And then once we've done that, once we've calculated the t derivative of that, then we'll have to divide by dx dt, which is 2t. All right. So now, if we were to calculate as written, we'd need to use the quotient rule, right? Because it would be, you know, low d high minus high d low over low squared, you know, the quotient rule. But I'd rather not use the quotient rule. So I'm going to perform some algebraic simplifications first, right? So before I calculate the derivative, I'll say, you know, I could divide that in and say that this is 3/2 t, and then minus 3/2 t to negative 1 over 2t. So that's just an algebraic step to make my life a little easier. And then now I can differentiate that with respect to t and get, in the numerator, I'd get 3/2. And then subtract, but becomes add. So 3/2. And then multiply by t to negative 2. And then over 2t. And then, you know, you can imagine continuing, right? So you could algebraically simplify this some more, and then you could make a concavity chart and say, oh, for these t's it's positive, for these t's it's negative, etc. Any question about this? This is okay? All right? Good. So now, we want to be able to do all of the calculus things that we can do with functions that are like y is f of x. So what we were just talking about is tangent lines and things like that. And what's another calculus thing that we want to be able to do with y is f of x besides tangent lines? We also want areas, right? That'd be nice. So what about area? So specifically, the situation that we know and that we're comfortable with is that if this is A and this is B, like that, and this is the plot of y is f of x. That's the plot of y is f of x. Then that area there is given by the formula integral a to b f of x dx. Right? So that's what we know. And then, you know, we learned about the fundamental theorem of calculus, which gives you a nice way to evaluate that quickly. But do understand that what that is saying is that this dx represents, sort of conceptually, it represents the base of a rectangle, and the f of x represents the height of a rectangle, right? So that's a base times height, and then the meaning, you know, the reason for that elongated s is because of summation, right? So what this formula, remember what it's saying, you're summing up infinitely many infinitesimal rectangles. We're cutting that area into rectangles, making an approximation, and then letting the number of rectangles become infinite, and the rectangles themselves infinitely fine. Now the question is that, well, what if we've got a thing, you know, what if we've got a plot, but instead of y being a function of x, rather, x and y are each functions of t. Then what will we do? So can you kind of see the problem? Okay. So what if it changes to this? What if we say, all right, now the picture looks like this. A and B, not really relevant. And then like this, blah. So now what we have there is that, say, well, each one of these points has coordinates x of t, y of t, if you like. And you might say that x is, you know, say f of t, and y is some other function, g of t. And just for sake of argument, to make our lives as simple as possible, I'll say that that point occurs at t0, and then, you know, we trace blah blah, and this is t1. So the question becomes is, you know, how do we get that area? How do we get it? All right. So in the end, we have to still do the base times height thing. We've still got to do that. So specifically, what I want you to observe is that concerning this formula, we don't usually write it this way, but after all, because y is f of x, in some sense we could write it like this. Okay, because that's base times height. So that's going to be the idea for this. That's going to be the idea for this. So now let's make the substitution. So how do we do it? All right. So specifically, we're going to say we're going to put g of t right there. But what do we replace with dx? Right. So what we're going to substitute, we're going to make this substitution into there. We're going to make that substitution into there. Y just gets replaced with g of t, but dx, because of this, because dx dt is f prime of t, that means what do we replace dx with? F prime of t dt. Okay. So then we could say that the formula must be, well, g of t, f prime of t dt, and then the limits just get replaced with t0 and t1. That's interesting. But do you observe that it's, again, just base times height? Okay, another matter that we wanted to be able to deal with, and we did deal with, was arc length. And remember how we did it. We said that, you know, if we've got, again, if I say that this is A and B, some function there, and then we could view it, if we view this as y is f of x, like so, y is f of x, and the question is you know, how long is that that red string if we could grab it and straighten it out? So remember how we did it. What we did is we said, well, we'll cut it into, say, like 8 line segments, approximate it with 8 line segments. And line segments have the virtue that, you know, you can calculate their length with the Pythagorean theorem. And then we said, well, that's not exact, so then let's actually view this, this curve as infinitely many infinitesimal line segments, and then find the length of each one of those line segments and add them all up. So the arc length would be integral a to b, and can anyone remember it? Right. 1 squared plus, of course 1 squared is 1, but I'll write it like that, and then what goes here? Yeah, dx, right? So then the question becomes is that, well, what if instead of y being a function of x, what if x and y are each functions of t? All right, so doing a similar kind of substitution, if this happens to occur at time 0, and this happens to occur at time 1, then we can make the exact same kind of substitution and obtain the following. That this would now be an integral. This would still be a square root. And here, in fact, instead of 1 squared plus dy dx all squared, it is an interesting exercise that I'll omit for time to show that this is the case. Which is why I always write 1 squared, to remind myself that what this is that's the Pythagorean theorem. That's the length of the hypotenuse of a triangle. And you know, the horizontal leg is dx dt. The vertical leg is dy dt. You square them, you add them, you square root. Yes?
Yes, just to ask, I don't know if we'll cover it next. Would it be nice to pertain to volume?
That we're going to skip that, but it's a good idea, right? Because in the end we want to like collect all of the, you know, basically anything that we can do with y as f of x, we want to be able to say that, and we can do it all when x and y are each functions of t. So we can calculate areas, we can calculate arc lengths. Beautiful. Any questions about this? So again, remember when we calculated arc lengths the first time, you know, we commented that basically all of these integrals are completely contrived, because the fact that you want to use the fundamental theorem means you have to anti-differentiate something that looks like antiderivative of square root, and unless it's just some special thing that suddenly makes the square root go away, you're not going to be able to do it. Good. Any question about that one? So maybe, what time is it? Okay, we'll start one of those. But we, you know, maybe we'll talk. No, we'll do that. We'll do it like this. Oh, that's boring. Now let's do this. So here's the question. I could say, all right, suppose that x is a multiplied by the cosine of t, and y is b multiplied by the sine of t, and also suppose that we have 0 less or equal t less or equal to pi. So because of our previous experience, you should know what this is. So what is this? What is it? Well, it has something to do with the Pythagorean identity. So specifically, a and b are just positive constants. So what is this? This is an ellipse, right? If they were both 1, then it would be exactly the unit circle. If they were both 4, it would be the circle of radius 4. If they were both 44, it would be the circle of radius 44. But this is the ellipse that has x radius a and y radius b. And is it all of the ellipse, like we're going to trace it all out, or we just trace part of it, or what?
The whole.
It's the whole thing, because we're doing a full angular measure, okay, going all the way around. So the question is find, well, we could ask two questions. We could say find the area. Find the area of that shape there. Well, that doesn't really make sense because some of it is below the axis. So I'll scratch that and say that instead let's find the arc length. All right. So the question doesn't specify which is greater, A or B, but just for concreteness, to draw a picture, I'll assume that x is the bigger one, so that the picture looks like this. so that x is the bigger one. And what we'd be asking is, how do you do that? Okay, so then I want you to we're basically out of time now, just about. So I guess let's set up the integral. So what would the integral be? Integral what? 0 to 2 pi. And then big square root, right? Big square root. And then what would go where? So what's dx dt? Nearly. What's the derivative of cosine? Negative sign. Of course, the negative squares away. All right. So, you could try and figure out, can you figure out how to evaluate that, assuming a and b are constant? And now suppose that I make a third question, which is a proper way to state this one. I could say find the area of that ellipse. And that means that I'm not interested in counting the bottom half as negative, but rather I want to count it all as positive. So how could you do it? I heard someone say it. Yeah, you could find the area of the top half and then double it. Okay, so let's write down that formula and then let's go. So twice, and then integral, and what would the limits be? 0 to pi, meaning that we're only going to do half of it. So then it would be y dx. Right? Y dx. So to substitute it in, we'd write y. Y gets directly substituted in, so b sine t. And then what is dx then?
Negative a sine t.
Very good. So multiplied by negative a sine of t. So that's that, and then dt. And again, that's y. Dx. So one of these will be quite easy to do, and one of them will not be. So please, over the weekend, for ungraded, please evaluate these, or try.